Okay, so let's drill a little bit deeper into this infinite dimensional RBF kernel, the Gaussian kernel, and I'll set the scale parameter gamma to be 1. So my kernel of x and x prime is equal to e to the minus x prime norm. Okay, just for simplicity. Now, remember, when you solve the dual version of the problem that uses only this kernel, which represents inner products, you get the alpha n's. Alpha n star. So this is a quick review of even last lecture. And the final hypothesis, g of x, so for the test input x, is equal to the sine of the sum from, and now I will explicitly say that, we only need to consider the sum over the support vectors, the data points for which the Lagrange multiplier alpha n star is positive. So alpha n star, some of them are 0, so we can throw these data points away. They have no role to play in the final classification. So, in some sense, useless data for the classification, for the final classifier. And then you've got alpha n star that are positive, okay? And you also have some alpha n stars that are C, okay? But the alpha n stars that are positive and strictly less than C are the support vectors. When the alpha n stars are C, those are the data points that penetrate the margin. Okay, and the alpha n stars that are in between 0 and C are the ones that are on the margin, that are on the cushion. Okay, so these are your support vectors. Okay, so the final classifier g of x is the sine over your support vectors. So alpha n star greater than 0, okay, of alpha n star yn. Good. Now we have the kernel, okay, the kernel of xn and x, your input. Okay, so this is W transpose x, okay, plus b star. And we already saw last time that we can compute this b star using only the kernel. It depends only on what are the support vectors and the inner products. Okay, so let's assume that we've computed b star. Okay, and in the case of the Gaussian kernel, this is equal to the sine of the sum of alpha n star greater than 0, alpha n star yn e to the minus, there's a squared here, e to the minus norm of xn minus x squared. Okay, and then you have a plus b. Now, I want to compare this. I want to show you a comparison between what the support vector machine produces and what we saw earlier, which we called the RBF network. So the RBF network. Okay, the final hypothesis g of x was equal to, okay, the sine of W0 plus W, the sum from, j equals 1 to k of wj e to the minus x minus mu j squared, where there would have been a scale parameter r squared, but I've just set that to 1, just so that we can compare apples to apples. Okay, so this is the RBF network. Let's compare. Wow, they look very similar. Okay, well, we have our b star here, which corresponds to W0, okay, and then we have a sum, okay, with certain weights, okay, and the Gaussian similarity measure. Okay, we have a sum, we have a bias, and then a sum with weights of the similarities between x and centers of my Gaussian bumps, okay, and weighted by Wj. Similarities between x and data points, okay, weighted by my Lagrange multipliers. So this plays the role of the Wj, okay, and this here plays the role of my mu j. Okay, and now, when we talked about the RBF network, we said, oh, okay, so you have to figure out k, for example, with cross validation. So figure out k, and then the mu j are constructed using unsupervised learning as centers of clusters. So mu j via unsupervised learning as cluster centers Okay, and then the Wj, W0 and Wj come from, treating this as a linear model and then running on whatever linear model algorithm we want. Fit as linear model. Okay, so that was the RBF. But look at what goes on here. Well, okay, it's exactly the same functional form. Okay, what is K? What is the number of centers? K. K is equal to the number of support vectors. Automatically determined. When we solved the optimal hyperplane algorithm, it automatically tells us what are the support vectors that will play a role here. So the number of non-zero Lagrange multipliers is exactly the number of terms in this sum. What are the centers? We don't have to learn with unsupervised learning. The centers are the support vectors. There, Xn. The centers are the support vectors. Very important data points. It makes a lot of sense. Okay, and so you can view this optimal, margin, maximum margin kernel machine as essentially an RBF network where the number of centers has been defined, has been determined for you, and the positions of those centers have also been determined for you. There's nothing for you to determine. It just spits out an RBF network. And we know that it is the maximum margin RBF network in some infinite dimensional space. So it's optimally regularized. Wow! Automatically determines the number of centers and automatically determines the centers, the position of those centers as data points, as in specifically support vectors. Bam! Okay. Just plug and play. Once you give me that kernel. Okay. Let me show you another learning model that we saw before. The neural network.